Hello everyone, welcome to this video. This video is kind of not really one big topic, it's kind of a collection of little things that don't really fit into their own short video, so I'm just going to do it in one. And we're going to cover basically three topics today. The first topic is air resistance, which is something we've kind of talked about a little bit before, but always in the context of saying how we're ignoring it. Well, today we're going to not ignore it. Secondly is Earth's gravity. Something we've definitely talked about a lot before, but we're just going to elaborate a little more on it. And thirdly, the difference between mass and weight. And we've kind of gone over this before, and I've said, that they're basically the same, but physics has kind of more specific definitions of the two. Now we're going to go into why mass and weight are actually very different. Now, up until now, they haven't really been. Now we're going to explain why they are. So these are kind of the topics that we're going to go through today. Before we start any of this, there's just one generic thing I want to explain that's kind of really relevant to all of them, and that is this formula. Force of gravity is equal to mass times gravity. And this is really just, a Newton's second law, force net equals mass times acceleration, where I put gravity, which is, if you remember, 9.8 meters per second squared, in as the acceleration. And this just tells us that if we have an object, whatever object it is, like this object right here, and we know its mass, maybe it's 10 kilograms, that we can calculate the force of gravity on it. We can go ahead and say, okay, force of gravity is going to equal the mass of 10 kilograms times that force of gravity, 9.8, and we could calculate it from there. And this is one important thing that's going to come up a lot. So, we're just going to underline it. Very important. Okay, on to today's different topics. Topic 1, air resistance. Air resistance is something that we keep talking about how we ignore. We always say, okay, these questions involving vertical motion, we ignore air resistance, or air resistance is negligible. Basically, it hasn't factored in at all. Today it's going to factor in, and we're going to kind of explore what air resistance is. Basically, when you have an object, and that object is falling through the sky, or going down vertically with this force of gravity, it's always propped up by an opposite force, which we can just say is the force of air. And this is literally the resistance that's in air to objects moving through it. You might have felt air resistance yourself if you ever try and go in like a race car or even just a normal car really fast and you stick your head out the window. You'll experience this phenomenon where your head gets actually physically pushed back by this, what we would call wind. But it's not really wind. It's just air resistance. It's the resistance of the air as the car is moving through it. And we experience air resistance lots of different places, but for us it really factors in when we're going to do problems with vertical motion. Because vertical motion, things falling down, deals with air resistance. And air resistance is an important component of vertical motion. So we're just going to explore what really happens. And if you remember, we've had discussions in the previous unit about terminal velocity. Here we're going to look at air resistance and how that kind of factors in. So when we start in a normal object and the object is falling, what we have is quite a large force of gravity. We know that this is 9.8 meters per second squared that it's accelerating at, and we know we can get that force based on the mass of the object, and this is our force of gravity. We also have this pretty minimal force of air resistance. The reason this is so small is because of what air resistance is based off of, and it's based off of two factors. One is what's called cross-sectional area, and the other one is called object speed, which is, literally the object speed. So we're going to look at these two things pretty briefly. Cross-sectional area is literally if you just had an object, the area underneath it kind of in 2D. And that area influences how much air kind of touches that object when it's moving downward, and therefore the bigger the cross-sectional area, the more air resistance. The other thing is the speed of the object, and this is pretty simple. The faster the object, the more air resistance. Okay, so given these two things, we can explain why in this diagram, air resistance is pretty small. The object just started moving, it's accelerating due to the force of gravity, but right now, the air resistance is pretty small. It just started moving. Now, as this goes on, air resistance is going to start to get bigger. You notice now it's a bigger arrow. And air resistance is bigger here, and it's going to go bigger and bigger and bigger, and at one very critical point, it is going to hit what we call terminal velocity, or sometimes terminal speed. Terminal velocity is this very specific point at which the force of air equals the force of gravity. And at this point, when these arrows are equal, we suddenly have no acceleration. Remember Newton's first law that says if there is no imbalance in forces, then the object is just going to stay at a constant velocity. And so when these things equal each other and the net force is therefore zero, this object is just going to keep moving at a steady velocity, and that velocity is called terminal velocity. It's going to move along like this for a little bit, but every time it does this, it continues to accelerate at the force of gravity. It's in its constant velocity, and now it's going to move out of terminal velocity, and you're going to get a phenomenon now which happens kind of in reverse. The air resistance is now going to get bigger as it goes faster, and force of gravity is going to imbalance more, and you're going to end up with this situation, and then this is going to go backward, and it's going to go more and more back to the original point. So basically, it's going to go into terminal velocity, and then it's going to come out of terminal velocity, and you're going to end up back with a slow speed, minimal air resistance, and then the object will land. This is how the flight of objects through air, say a skydiver, really works. You start with minimal air resistance, you go to a point where you hit terminal velocity, and then you go back. Force of gravity, of course, always very constant, but there's this critical point here where these forces are balanced at terminal velocity. That's basically the gist of air resistance and how it's important in terms of terminal velocity. Like most of the topics we do in these videos, it starts to make a significantly more sense when we look at problems involving it. For now, this is really all you need to know. Okay, our next topic is the topic of Earth and its gravity. There's just a couple facts really that are nice to know here. Gravity is the only one of the forces we've dealt in this unit which is non-contact, and we talked about this in our first ever video. Non-contact forces mean that they do not need to have objects touching for the force to work. In fact, gravity works using a force field. The center of the Earth literally just exerts this force in all directions around the Earth, and you could be over here on the Earth, or you could be over here on the Earth, and it doesn't matter. You're not touching the object, which is arguably the core of the Earth, but you're just experiencing this force field that radiates around the Earth. And you can only obviously receive this force if you're in the region that the field kind of exists in. So obviously if you're a star over here, you're not experiencing the gravitational pull of the Earth. And so the Earth is really surrounded by this field of gravity that keeps everything on the Earth. We literally have lines of force all going toward the Earth's center. The further you are from the Earth's surface, you get a less and less and less of a force of gravity. The weaker the force of gravity is experienced. So by the time you're out here, you basically have nothing. There's no force of gravity. But on Earth, we get our strong force of gravity that we measure at about 9.8, that magic number. Meters per second squared is the acceleration, and the newtons obviously depends on the mass. Then this brings back this equation, which is the force of gravity equals mass times gravity. Remember that this is 9.8 meters per second squared, which we can use to calculate the force of gravity for us humans on the planet Earth. And that force could be different if you're on Mars or if you're in the middle of the solar system. Who knows? But for us, it's 9.8 meters per second squared in a down direction. Okay. That's about it for this topic. let's move on to our last topic. The final topic, and arguably the most important one, is this distinction between the ideas of weight and of mass. Weight and mass are these two concepts that we continue to discuss as being kind of very similar, but they really have an important distinction between them. Here's weight and here's mass. Let's kind of look at that difference. So mass, physicists consider mass to be the amount or the quantity of matter that's in an object. So if you have an object, here it is, it has a certain amount of matter in it, kind of like atoms and molecules, etc. And this is the mass of the object. The unit of mass is kilograms, or, grams, etc., all those things that have gram in them, but kilograms is the usual one we use. We measure mass using like a balance or a scale, and the only way that you can change a mass in any time is by physically changing the amount of matter. If this is some sort of like scoop of ice cream, if you remove some of the scoop of ice cream, well, its mass goes down. Now you have a smaller amount of mass. The mass of a collection of sand, if you remove some of that sand, you have less mass. But mass is a very physical quantity. It's measured in kilograms, and you can't really do anything to change it besides literally just removing or adding the matter. So mass is the quantity of matter in an object. Now, a lot of people will think, oh, weight is also this thing. And, that's an okay thing to think initially, but weight is actually very different. Weight is the measure of the force of gravity on the object. Now, you hear this and you're like, what? Weight is the force of gravity? That makes no sense. But weight and force of gravity are the same thing. Literally, so much the same thing we can just say they equal each other. Weight equals the force of gravity. And this is the weight of an object, and it equals the force of gravity for an object. And if we recall, that's the mass of the object times the acceleration due to gravity. Now, that means a couple things that we didn't really think before. One of them is that weight is a vector. It has a direction. Because it's gravity, that direction is typically down, but nonetheless, weight has a direction. Secondly, weight is not measured in kilograms, it is measured in newtons, the unit we use for force. And that's because it literally is a force. It's the force of gravity acting on an object. You might have heard that famous thing about how astronauts who went to the moon could jump really high and kind of float around because they weighed less. And you might have wondered, well, how did they weigh less? I thought weight was just kind of how much an object has in terms of matter. And that is the key difference between mass and weight. Their mass never changed. You can't change the mass of a person unless you, cut off their head. Whereas the weight can change because the gravitational force on other planets, for instance, the moon, not a planet, I know it's a moon, is about 1/6 of Earth, which means that it is significantly less, and therefore everything weighs less. Weight is always relative not only to the mass of the object, but also to the force of gravity. That means that we can measure weight on our Earth always relative to this number of 9.8. We just take the mass of an object, say it's 10 kilograms, and we multiply it by 9.8 meters per second squared. And you'll arrive at an answer of a certain number of newtons, and that is a weight. And we can do that. But that number is completely invalid if we bring ourselves to Mars or to Venus or to some other place where gravity is different. All of a sudden we're experiencing a different value here, and that will affect the value of weight. So that's kind of a big deal to understand, is that weight is not based only on mass, it also is affected by gravity. A bathroom scale measures your weight, and it measures it literally by measuring the normal force, the force that you're exerting on contact with it. Because the weight is dependent on gravity, and it uses the gravitational force that it's experiencing and measures that force to determine, oh, you weigh a certain number of kilograms, or pounds if you're using imperial, and it creates that calculation. So this is one of the most foundational things to understand, and we kind of left it for last here, but it's very important to understand the difference between weight and mass. Mass is an absolute quantity. You can't really change it without changing the object itself. But weight is a force, and you can affect that by just changing the gravitational force that is felt. Again, like every other concept today, this begins to make significantly more sense when we do practice problems with weight or mass. And we will definitely do those in the future. But for now, the most important thing to understand is just how to explain these concepts. Weight being equivalent to the force of gravity, and mass being a measure of the quantity of matter. That's about it for this video. It was just kind of a collection of oddball topics, and we're nearing the end of all the concepts in this unit, so I just wanted to get those all down so that they're really clear. That's about it. Thank you for watching, and I'll see you again next time.